Let's discuss highest weight modules of semisimple Lie algebras. Semisimple Lie algebra G can be decomposed in terms of a part which has as weights the positive roots with respect to a Cartan subalgebra H, and another part which corresponds to the negative roots. So now, what is a highest weight module? Suppose we have a UG module M. We say that V plus is a maximal or primitive vector of weight lambda if, of course, V plus is an element of the weight space, and we demand that n annihilates the vector V plus. So then this is maximal because we can no longer raise the weight. Now, M is a highest weight module if it is entirely generated from such a maximal vector. That is to say, we have V plus such that UG acting on V plus is equal to the highest weight module M. Of course, this is equivalent to the statement that M is equal to U, universal enveloping algebra of n minus, acting on V plus, because H acts diagonally and annihilates it, so only n minus acts. Here are some properties of highest weight modules. So first of all, the weight diagram looks like this with some highest weight, and then we descend in weight space. Each of these weight spaces is finite dimensional. We have that each quotient of such a highest weight module is again a highest weight module of weight lambda. A submodule generated by the highest weight, no, a maximal vector mu with highest weight mu smaller than lambda is obviously proper. It has a unique maximal module, which is the sum of all its proper submodules. And it has a unique simple quotient, namely by the maximal module. And it is indecomposable. Let me briefly recall that simple means there's no proper submodule, and indecomposable means that we cannot write it as the direct sum of two non-zero submodules. Moreover, all simple modules of highest weight lambda are isomorphic, and there's only one endomorphism basically between such simple highest weight modules. But this is an infinite dimensional generalization of Schur. So these are some properties of highest weight modules. But now let's construct a prime example. These are called the Verma modules. So suppose we pick some Borel subalgebra B, which is basically H plus N, and pick a one-dimensional representation of this Borel subalgebra. of weight lambda. So this tells us how H acts, and moreover n annihilates it. So again, we have here highest weight vector of weight lambda. But now we define the Verma module explicitly. What is it? It is UG tensor with UB made trivial with C lambda. This is the Verma module of weight lambda. It is clearly equal to U n minus acting on V lambda. So this module clearly has a highest weight vector V lambda, or maximal vector V lambda. And moreover, it has a universal property, because if I consider the ideal I, which annihilates a highest weight vector V lambda, then M lambda is universally defined in terms of V lambda as just UG divided by this ideal. And therefore, M lambda is universal. Namely, only depends on V lambda or lambda. So M lambda is a universal construction. So we summarize a little bit. We have a Verma module M lambda defined universally in terms of the highest weight lambda. We have a unique simple quotient, which we will denote by L lambda. And we will have a unique maximal proper submodule, which we will denote by n lambda, and m lambda divided by n lambda is L lambda. Very good. Now I want to broaden our perspective once more and put this into the context of the BGG category O, which I've introduced elsewhere. In the context of the BGG category O, we can now say that any module M in O has a finite filtration of the type where I have consecutive submodules such that there's a finite number of them, the last one is M, and moreover, mi plus 1 divided by mi is a highest weight module. The way this is proven is, well, M is finitely generated, it's locally UN finite, and therefore with some finite number of possible highest weight vectors, we can take the highest one and then mod out by the module generated by the highest one. We'll be left with some smaller piece. So this one was the whole M. We'll be left with some smaller piece, which will function as M n minus 1, etc. And because there's a finite number of these highest weight vectors, this chain ends. Moreover, it is now not too difficult to prove that every simple module in the category O is isomorphic to a simple module L lambda that we obtain by dividing a Verma module by its maximal proper submodule. It is interesting to continue this analysis, for instance, by examining the structure of maximal vectors inside Verma modules.